Close your eyes for a moment and imagine a world utterly unlike anything you've ever experienced. There are no forests, no mountains as we know them, no blue skies stretching endlessly overhead. There are no oceans gently lapping at sandy shores, no rain falling softly through the atmosphere. Instead, picture a sphere of molten rock suspended in the void of space, its surface a roiling sea of liquid stone glowing with the fierce orange and red hues of extreme heat. This is Earth, but not as we know it. This is Earth in its infancy, during the most mysterious and violent period of our planet's long history. We call this time the Hadean Eon, named after Hades, the Greek god of the underworld. The name alone tells you something about what scientists initially imagined this period to be like. A hellish, inhospitable nightmare of a world where nothing could possibly survive. And yet, this violent beginning was absolutely essential for everything that came after. Without the Hadean, there would be no blue marble floating in space, no life, no us sitting here contemplating our origins. The Hadean Eon spans a vast stretch of time from approximately 4.6 billion years ago to about 4 billion years ago. That's roughly 600 million years, or more than 100 times longer than the entire existence of our species. To put this in perspective, if we compressed all of Earth's history into a single year, the Hadean would occupy the first 2 weeks of January. During those 2 weeks, our planet transformed from a collection of cosmic debris into something recognizable as a proper world, complete with a solid surface, an atmosphere, and even oceans. But here's what makes the Hadean so fascinating and frustrating in equal measure. We have almost no direct evidence of this time. The relentless forces of plate tectonics, weathering, and geological recycling have erased nearly all physical traces of Earth's earliest history. The rocks that formed during the Hadean have been ground down, melted, subducted, and metamorphosed beyond recognition. What little evidence we do have comes from a handful of tiny mineral crystals called zircons, found in a remote region of Western Australia, and from studying the cratered surfaces of the Moon and other bodies in our solar system that have preserved their ancient scars. So how do we know anything about the Hadean at all? Scientists have become incredibly clever at reading the subtle clues preserved in these ancient zircons, in the chemistry of rocks from slightly later periods, in computer simulations of planetary formation, and in observations of young solar systems forming around distant stars. It's like trying to reconstruct an entire novel from a few scattered words on burned pages. But the story that emerges is absolutely extraordinary. The Hadean began with the birth of our planet itself, coalescing from the swirling disk of dust and gas that surrounded our young sun. It was a time of constant bombardment, when asteroids and comets rained down upon the growing Earth with devastating frequency. It witnessed the most catastrophic impact in our planet's history, a collision with a Mars-sized body that created our moon. It saw Earth's interior separate into distinct layers, with heavy metals sinking to form the core, while lighter materials rose to create the mantle and eventually the crust. And contrary to what scientists long believed, evidence now suggests that even during this supposedly hellish time, liquid water existed on Earth's surface, pooling into primitive oceans beneath a thick, steamy atmosphere. The story of the Hadean is the story of how a planet is built from scratch, how order emerges from chaos, and how the stage was set for the most remarkable development in our solar system's history, the emergence of life. So let's journey back through deep time, back beyond recorded history, beyond the evolution of complex life, beyond even the formation of the oldest rocks we can hold in our hands, to witness the birth of our world. To understand the Hadean Eon, we first need to understand how our entire solar system came into being. The story begins not with Earth, but with a vast, dark cloud of gas and dust drifting through the emptiness of space. This molecular cloud, measuring perhaps dozens of light years across, was composed primarily of hydrogen and helium, the leftover material from the Big Bang itself, along with heavier elements forged in the hearts of earlier generations of stars that had lived, died, and exploded as supernovae, seeding the cosmos with the building blocks of everything we see today. Something disturbed this cloud. Perhaps a nearby star went supernova, sending shockwaves rippling through space. Perhaps the cloud simply grew massive enough that its own gravity could no longer be resisted. Whatever the trigger, about 4.6 billion years ago, a portion of this cloud began to collapse in on itself. As it collapsed, it began to spin, like a figure skater pulling in their arms. The cloud flattened into a disk, with most of the material falling toward the center, where temperatures and pressures began to rise dramatically. At the heart of this collapsing disk, something remarkable was happening. The center was growing denser and hotter with each passing moment as more and more material piled on. Eventually, the temperature and pressure at the core reached a critical threshold, about 10 million degrees Celsius, and hydrogen atoms began to fuse together into helium. This nuclear fusion released tremendous amounts of energy. Our sun had ignited, but the sun didn't consume all the material in the original cloud. A significant amount remained in the flattened disk surrounding the newborn star. This is what we call the proto-planetary disk, and it's where Earth and all the other planets would eventually form. The disk was a turbulent, chaotic place. It contained dust grains no bigger than particles of smoke, along with larger chunks of ice and rock. The temperature varied dramatically depending on distance from the sun. Close to the star, it was scorchingly hot, hot enough to vaporize most materials. Farther out, in the regions where the gas giant planets would form, it was cold enough for water, ammonia, and methane to freeze solid. In this disk, the process of planet formation began almost immediately. It started small, with dust grains bumping into each other and sticking together through electrostatic forces and the weak pull of gravity. As these clumps grew larger, their gravity became stronger, allowing them to attract more and more material. Within perhaps 100,000 years, the disk contained countless small bodies, ranging from pebbles to boulders, to objects several kilometers across. We call these early building blocks planetesimals. The planetesimals continued to collide and merge. Some collisions were gentle enough that the objects stuck together, growing larger. Others were violent, shattering both bodies into fragments that would later be incorporated into other growing worlds. It was a brutal, chaotic process, but gradually, out of the chaos, order began to emerge. Certain planetesimals grew faster than others, either because they happened to be in regions with more material or simply by chance. These became what scientists call planetary embryos, objects perhaps the size of our moon or Mars. In the inner solar system, where Earth would form, the temperature was too high for water ice to condense. Only materials with high melting points, silicates and metals, could exist in solid form. This is why the inner planets, Mercury, Venus, Earth and Mars, are rocky worlds, while the outer planets became gas giants. The composition of these early planetesimals and embryos in the inner solar system would have been similar to certain types of meteorites we still find today. Combinations of rock and metal, with iron and nickel for the metal component, and various silicate minerals for the rocky portion. The formation of these planetary embryos took somewhere between 10 and 100 million years. During this time, The protoplanetary disk was still rich with gas, and this gas created drag forces that affected the orbits of the growing planets. The disk also contained vast numbers of smaller objects, the leftovers from planet formation, that continued to bombard the growing worlds. Computer simulations of this process reveal something fascinating and somewhat terrifying. The final stages of planet formation were characterized by giant impacts between the planetary embryos themselves. These weren't gentle mergers. These were cosmic catastrophes that could partially or completely melt the colliding bodies, sending sprays of vaporized rock into space and fundamentally reshaping both the impactor and the target. Our solar system once contained perhaps dozens of these embryos, but through this brutal process of collision and consolidation, they eventually merged to form the 4 rocky planets we see today. Earth itself was built up through this process. Rather than forming gradually and gently, our planet assembled in a series of increasingly large impacts. Each collision added mass to the growing proto-Earth, but it also added tremendous amounts of energy. When a large object traveling at tens of kilometers per second slams into a planet, the kinetic energy of that impact is instantly converted into heat. This heat was one of several energy sources that kept the early Earth molten, as we'll explore shortly. The protoplanetary disk didn't last forever. The solar wind, the stream of charged particles constantly flowing outward from the sun, gradually blew away the remaining gas. Most of the small debris was either swept up by the growing planets or ejected from the solar system entirely through gravitational interactions. Within about 10 million years of the sun's ignition, the disk had largely cleared, leaving behind the configuration of planets we know today, along with the asteroid belt, a region between Mars and Jupiter where planet formation was disrupted by Jupiter's enormous gravitational influence. But planet formation wasn't quite finished. Even after the main phase of growth was complete, the inner solar system remained a crowded, dangerous place. Countless asteroids and comets continued to orbit the sun, crossing the paths of the newly formed planets. For hundreds of millions of years, these objects continued to rain down upon Earth and its neighbors, in what would later be termed the Late Heavy Bombardment. But we're getting ahead of ourselves. First, we need to understand how Earth itself took shape during those violent early days. The early Earth, what scientists sometimes call proto-Earth or Tellus, began as nothing more than one of many planetary embryos orbiting in the inner solar system. Over the course of tens of millions of years, this particular embryo grew through the accumulation of smaller planetesimals and through mergers with other embryos, gradually becoming the dominant body in its orbital zone. The process of planetary accretion is driven by gravity, but it's not a simple or straightforward process. Imagine 2 large objects orbiting the sun in similar but not identical orbits. Eventually, their paths will cross. What happens next depends on several factors: their relative velocities, the angle of impact, and their sizes. In some cases, the collision might be gentle enough that the objects stick together, combining their mass. In other cases, the impact might be so violent that both objects are shattered, sending fragments flying in all directions. Computer models of planetary accretion suggest that Earth grew through a combination of these processes. Small planetesimals were constantly raining down on the growing proto-Earth, adding their mass bit by bit. Occasionally, much larger impacts occurred, collisions with embryos that might have been a significant fraction of Earth's current mass. Each of these giant impacts was a catastrophic event that would have partially or completely melted the planet's surface, creating vast magma oceans and potentially vaporizing substantial portions of both the impactor and the target. As proto-Earth grew, several important processes were occurring simultaneously. One of the most crucial was planetary heating. You might think that as an object moves away from the sun, it should cool down, but the opposite was true for the growing Earth. Multiple heat sources were working to keep proto-Earth scorchingly hot. The first source of heat was gravitational compression. As more and more material accumulated on proto-Earth, the weight of the overlying layers compressed the interior. This compression released energy in the form of heat, in much the same way that a bicycle pump gets warm when you compress air inside it. The larger Earth grew, the stronger its gravitational field became, and the more heat was generated through this compression. The second major heat source was the impacts themselves. Every planetesimal that struck proto-Earth was traveling at enormous velocities, typically tens of kilometers per second. When these objects hit, their kinetic energy was converted into heat. Small impacts heated the surface. Large impacts generated so much energy that they could create vast pools of molten rock, sometimes hundreds of kilometers deep. The biggest impacts released enough energy to vaporize huge volumes of rock, creating temporary atmospheres of rock vapor that eventually cooled and rained back down to the surface. The third heat source was radioactive decay. The planetesimals that built up Earth contained certain radioactive isotopes, atoms that spontaneously decay into other elements, releasing energy in the process. Some of these isotopes, like uranium-238 and thorium-232, decay very slowly and continue to generate heat in Earth's interior today. But in the early solar system, there were also short-lived radioactive isotopes, like aluminum-26, that generated heat much more quickly before decaying away. These short-lived isotopes were particularly important in the early heating of planetary bodies. All of this heat had profound consequences for proto-Earth's structure and evolution. Rather than being a solid ball of rock and metal, the growing planet was at least partially molten for much of its early history. Different models predict different degrees of melting, ranging from a relatively thin molten layer at the surface to complete melting of the entire planet. The reality was probably somewhere in between, with the degree of melting varying over time depending on the timing and size of the most recent large impacts. This molten or partially molten state was crucial for what would happen next. In a solid body, different materials are frozen in place wherever they happen to be. But in a liquid, denser materials can sink, while lighter materials can rise. Proto-Earth contained a mixture of materials with very different densities. The metallic iron and nickel that made up a portion of the incoming planetesimals had a density about twice that of the silicate rock that formed the bulk of the material. In a molten or partially molten planet, these dense metals would sink toward the center, while the lighter silicates would rise toward the surface. This process, which scientists call planetary differentiation, or sometimes the iron catastrophe, was one of the most important events in Earth's early history. It transformed Earth from a homogeneous mixture of materials into a layered body with a dense metallic core surrounded by a rocky mantle, and eventually a thin crust at the surface. We'll explore this differentiation process in more detail in a later section, but it's important to note that it was happening, at least in stages, during the growth of proto-Earth itself. By the time proto-Earth had accumulated most of its current mass, it would have been a formidable world. Larger than Mars, but probably somewhat smaller than Earth is today, it orbited the Sun at roughly the same distance we do now. Its surface was a mixture of solidifying lava flows and impact craters, constantly being reshaped by new impacts. It had a thin atmosphere, primarily composed of gases released by volcanic activity and impacts, water vapor, carbon dioxide, and smaller amounts of nitrogen and other gases. This atmosphere was probably not stable, much of it would have been lost to space, either blown away by impacts or lost through atmospheric escape processes. But Proto-Earth was not alone in its orbital zone. Other planetary embryos continued to orbit the Sun in similar regions of space. Gravitational interactions between these bodies were constantly perturbing their orbits, making the system unstable. It was only a matter of time before another major collision occurred. And when it did, it would be the most important impact in our planet's history. The impact that would create our moon and give Earth its final major infusion of mass and energy. Before we examine that crucial event, it's worth taking a moment to appreciate the incredible journey that matter takes during planet formation. The iron and nickel atoms that would eventually sink to form Earth's core were forged billions of years earlier inside massive stars that exploded as supernovae. The silicon and oxygen that form the bulk of Earth's rock were created in similar stellar furnaces. These atoms drifted through space for eons, eventually finding their way into the molecular cloud that would birth our solar system. They were incorporated into dust grains in the protoplanetary disk, then into planetesimals, then into planetary embryos, and finally into the growing Earth. And their journey was far from over. Some of those atoms now reside in the mountains you can see on the horizon, in the oceans, in the air you breathe, perhaps even in your own body. We are, quite literally, made of stardust, and the Hadean Eon is a crucial chapter in the story of how that stardust came together to form a world capable of supporting life. Among all the dramatic events that characterize the Hadean Eon, one stands out as the most consequential. A collision between Proto-Earth and another planetary embryo that scientists have named Theia, after the Greek Titan, who, in mythology, was the mother of the moon goddess Selene. Based on various dating methods and computer models, this impact appears to have occurred somewhere between 4.5 and 4.52 billion years ago, roughly 50 to 100 million years after the formation of the solar system. This collision would reshape Proto-Earth, create our moon, and set the stage for much of what makes Earth unique among the planets in our solar system. Theia's origins remain somewhat mysterious, but computer models give us clues about where it came from and how it found itself on a collision course with Proto-Earth. Theia was likely similar in size to Mars, with a diameter perhaps half that of Earth, and a mass roughly 10% of Proto-Earth's mass at the time of collision. Like Proto-Earth, Theia had formed through the accumulation of planetesimals in the inner solar system and had probably undergone at least partial differentiation, meaning it had its own iron-nickel core surrounded by a rocky mantle. One intriguing hypothesis suggests that Theia may have formed at one of the Lagrangian points in the Earth-Sun system. Lagrangian points are special locations in the orbital paths of two large bodies, where a smaller object can maintain a stable position. The L4 and L5 Lagrangian points, located 60 degrees ahead of and behind Earth in its orbit, are particularly stable. If Theia formed at one of these points, it would have orbited the Sun in nearly the same orbit as Proto-Earth, but safely offset by this 60-degree separation. This configuration could have remained stable for millions of years, but as Theia continued to grow, eventually exceeding about 10% of Earth's mass, its gravity would have become strong enough to destabilize this arrangement. Gravitational perturbations from other planets, particularly Venus, could have nudged Theia out of its safe Lagrangian haven and onto a trajectory that would eventually intersect with Proto-Earth's orbit. The collision itself would have been a spectacle beyond anything we can truly imagine. Theia approached Proto-Earth at a velocity of several kilometers per second, not fast enough for a head-on collision to completely destroy both worlds, but certainly fast enough to make this a catastrophic event. The latest computer simulations suggest the impact may have been more direct than scientists previously thought, though there's still debate about whether it was a head-on collision or a glancing blow at an angle of perhaps 45 degrees. The moment of impact would have lasted only minutes, but in those minutes, the fates of both worlds were sealed. The first contact between the two bodies would have sent shockwaves rippling through both Proto-Earth and Theia. Rock that had been solid moments before was subjected to such extreme pressure and heat that it turned to liquid, then to vapor. The impact generated temperatures in the millions of degrees, hot enough to vaporize substantial portions of both the impactor and the target. Most of Theia was destroyed in the impact. Its iron-nickel core, denser than the surrounding rocky material, punched its way through Proto-Earth's mantle and merged with Proto-Earth's core. This process added about 10% to Proto-Earth's mass and contributed to the final differentiation of Earth's core. Recent studies have suggested that large fragments of Theia's rocky mantle may have survived the collision and now exist as massive, dense blobs deep in Earth's mantle. The large, low shear velocity provinces that seismologists have detected in the deepest parts of the mantle beneath Africa and the Pacific Ocean. But not all of Theia merged with Proto-Earth. A significant amount of material from Theia's outer layers, along with a substantial portion of Proto-Earth's mantle, was flung into space by the violence of the collision. This ejected material formed a massive disk of debris orbiting the newly enlarged Earth. The disk consisted of a mixture of molten rock droplets, vaporized rock that would later condense into solid particles, and perhaps some larger fragments that had been torn from the mantles of both bodies. The energy released by this impact was staggering, equivalent to trillions of the most powerful nuclear weapons humans have ever created, all detonated simultaneously. This energy partially or completely melted both Proto-Earth and Theia. Some models suggest that Earth was left with a global magma ocean, perhaps hundreds of kilometers deep. Other models propose that the entire planet was molten, a roiling sphere of liquid rock with surface temperatures exceeding 2,000 degrees Celsius. The impact also dramatically affected Earth's rotation. The angular momentum imparted by the collision set Earth spinning much faster than it does today. Based on models of the impact and subsequent tidal evolution, immediately after the impact, a day on Earth may have lasted only 5 to 6 hours, though the exact post-impact rotation rate depends on the details of the collision. This rapid rotation, combined with the gravitational pull of the newly forming moon, would help determine Earth's final obliquity, the tilt of its rotation axis relative to its orbital plane around the Sun. Evidence for the giant impact hypothesis comes from multiple sources. One of the most compelling pieces of evidence is the composition of the moon itself. The moon has a much smaller iron core than Earth, proportionally speaking, and is deficient in volatile elements, substances that evaporate easily at high temperatures. This makes perfect sense if the moon formed from material that came primarily from the outer layers of Proto-Earth and Theia, rather than from their cores, and if the material went through a period of extreme heating that drove off many of the volatiles. Another line of evidence comes from isotopic analysis. For many years, scientists noted that moon rocks brought back by the Apollo missions had almost identical isotopic ratios to Earth rocks for many elements, including oxygen, titanium, and tungsten. This was puzzling because we would expect Theia, having formed in a potentially different part of the solar system, to have a different isotopic signature. Recent high-precision measurements have revealed subtle differences in some isotopic ratios between Earth and the Moon, supporting the idea that Theia contributed material to both bodies. The high degree of similarity can be explained if Theia formed in a very similar region of the protoplanetary disk to Proto-Earth. or if the extreme conditions of the impact thoroughly mixed and homogenized the material. The isotopic similarities also place constraints on the nature of the impact and the subsequent formation of the moon. Some researchers have proposed that the extreme heat and vaporization caused by the impact created what scientists call a synestia, a donut-shaped cloud of vaporized and molten rock surrounding proto-Earth, from which both the final Earth and the moon would have condensed. This model could help explain why Earth and moon materials are so thoroughly mixed, though the synestia hypothesis is still being refined and tested. The timing of the giant impact has been refined through various dating techniques. By analyzing the crystallization ages of rocks from the moon and using computer models of the dynamical evolution of the early solar system, scientists have determined that the impact occurred roughly 50 to 100 million years after the formation of the solar system itself. This means that, at the time of impact, proto-Earth had already accumulated most of its mass and had likely undergone significant differentiation. The giant impact was not unique to Earth. Evidence suggests that many, perhaps most, of the final stages of planetary formation were characterized by such catastrophic collisions between planetary embryos. Mercury may have lost much of its rocky mantle in a similar giant impact, which would explain its unusually large iron core. Uranus and Neptune are tilted dramatically on their sides, which could be the result of giant impacts in the outer solar system. Earth and Theia simply represent one example of a common process in planet formation. The consequences of the Theia impact extended far beyond just creating the moon. The collision reset many of Earth's evolutionary clocks. Any atmosphere that proto-Earth had accumulated before the impact would have been blasted away into space. Any chemical differentiation that had occurred in proto-Earth's mantle was partially or completely erased by the thorough mixing caused by the impact. In a sense, the giant impact gave Earth a fresh start, creating a newly molten world that would have to cool and differentiate all over again. The disk of debris that formed around Earth after the Theia impact was a temporary structure, but from it would emerge one of the most important features of our planet, the moon. Understanding how this disk coalesced into a single large satellite helps us appreciate both the violence of Earth's early history and the delicate balance of forces that shaped our planetary neighborhood. Immediately after the impact, the debris disk was an incredibly hot and violent environment. It consisted of a mixture of molten rock droplets, vaporized rock, and possibly some larger fragments, all orbiting Earth in a flattened disk. The inner part of the disk, closest to Earth, was hottest and primarily composed of vapor. Farther out, temperatures were low enough for material to exist as molten droplets or even solid fragments. The disk was also extremely dense compared to Earth's current moon, containing enough material to form a body with the mass of our moon, and perhaps additional material that would later fall back onto Earth. The formation of the moon from this disk was remarkably fast by geological standards. Computer simulations have produced varying estimates. Some recent high-resolution models suggest the moon could have formed in just a matter of hours, while other models indicate timescales ranging from a few decades to several thousand years. Regardless of the exact duration, this was essentially instantaneous compared to the millions of years required for the initial formation of Earth itself. The process began with the debris in the disk colliding and sticking together. Unlike the formation of planets from the protoplanetary disk, which was a chaotic process involving objects on intersecting orbits, the material in the post-impact disk was all orbiting in roughly the same plane at similar velocities. This meant that collisions were relatively gentle, allowing particles to accrete rather than shatter upon impact. As clumps of material in the disk began to grow, they started to gravitationally interact with each other. Larger clumps attracted more material, growing faster in a runaway process. Eventually, one or perhaps a few large bodies began to dominate, accreting most of the mass in the disk. These proto-moonlets continued to grow and to gravitationally interact with each other. If multiple large moonlets formed, they would have eventually collided and merged, since their orbits were all confined to a relatively narrow disk. There's an ongoing debate in the scientific community about exactly how the moon reached its current orbit. Some models suggest the moon formed close to Earth, perhaps only a few times Earth's radius away, and then migrated outward due to tidal interactions with Earth. Other recent simulations suggest that the moon could have formed immediately in an orbit much farther from Earth, depending on the details of how the disk spread out after the impact. Tidal interactions between Earth and the moon have been crucial throughout the moon's history. The moon's gravity creates bulges in Earth, both in the oceans and in the solid Earth itself. Because Earth rotates faster than the moon orbits, these bulges are carried ahead of the line connecting Earth and the moon. The gravitational pull of these bulges on the moon acts to speed up the moon's orbital velocity, causing it to spiral slowly outward. Meanwhile, the moon's gravity pulling back on these bulges acts to slow Earth's rotation. This is why Earth's day has gradually lengthened over geological time, and why the moon continues to recede from Earth at a rate of about 4 centimeters per year. Shortly after its formation, the moon would have been much closer to Earth than it is today, perhaps orbiting at a distance of only 15 to 20,000 kilometers, compared to the current distance of about 384,000 kilometers. At this proximity, the moon would have appeared enormous in Earth's sky, perhaps 20 times larger than it appears to us today. The tides it raised on Earth would have been correspondingly more extreme, potentially creating tidal bulges tens or even hundreds of meters high in Earth's oceans. The moon itself would have been a dramatically different world in its earliest days than it is now. The gravitational forces from nearby Earth, combined with radioactive heating and possibly the heat left over from its formation, would have kept much of the lunar interior molten. The moon may have had its own magma ocean, a global layer of molten rock, perhaps hundreds of kilometers deep. This magma ocean would have gradually cooled and crystallized, with denser minerals sinking and lighter minerals rising to form the moon's earliest crust. Evidence for this lunar magma ocean comes from the composition of the rocks brought back by the Apollo missions. The lunar highlands, the lighter-colored, heavily cratered regions that cover much of the moon's surface, are composed primarily of a rock type called anorthosite, which is rich in a mineral called plagioclase feldspar. Plagioclase is less dense than the other minerals common in basaltic magma and would have floated to the surface of a magma ocean, forming a thick crust. The darker maria, the large impact basins that give the moon its characteristic face, were filled in later with basaltic lava flows, but the presence of the anorthositic highlands suggests that the moon went through a period when much of its surface was molten. The formation of the moon had profound effects on Earth itself. First, and most obviously, it gave Earth a large natural satellite, unusual for a rocky planet in the inner solar system. Mercury and Venus have no moons, and Mars has only 2 tiny captured asteroids. The presence of a large moon has helped stabilize Earth's axial tilt over geological time. Without the moon, Earth's obliquity would vary much more chaotically due to gravitational perturbations from the other planets, particularly Jupiter. This stability in Earth's tilt has been crucial for maintaining a relatively stable climate over billions of years, which may have been important for the evolution of complex life. Second, the moon's tidal influence has been important for Earth's oceans and potentially for the evolution of life. Tides create mixing in coastal environments and may have helped concentrate organic molecules in tidal pools, potentially assisting in the origin of life. The tidal slowing of Earth's rotation has gradually lengthened our day, which has had various effects on Earth's climate and the evolution of life. Third, the moon may have acted as a shield, intercepting some of the asteroids and comets that would otherwise have struck Earth. While this effect shouldn't be overstated, the moon is small compared to Earth and doesn't provide that much protection. It has likely reduced the number of impacts Earth has experienced over its history. The moon also serves as a crucial record of solar system history. Because the moon has no plate tectonics, no atmosphere to speak of, and minimal weathering, its ancient surfaces are preserved in a way that Earth's surfaces are not. The heavily cratered lunar highlands date back more than 4 billion years, to the late Hadean and early Archean. By studying these surfaces and the rocks brought back by the Apollo missions, scientists can reconstruct the bombardment history of the inner solar system, information that has been largely erased from Earth's surface but is crucial for understanding the Hadean environment. Recent research has continued to refine our understanding of the moon's formation. High-resolution computer simulations using more sophisticated physics have suggested new scenarios, including the possibility that the moon formed much more quickly than previously thought, perhaps in just a few hours rather than years. These simulations also suggest that more of Earth's mantle material may have contributed to the moon than earlier models predicted, which would help explain the isotopic similarities between Earth and moon rocks. The moon we see today, silvery and cratered, bearing the scars of billions of years of impacts, is a far cry from the glowing ball of molten rock that first coalesced from the debris disk around proto-Earth. But it serves as a constant reminder of the violent processes that shaped our planet, and of the cosmic accident that gave Earth its most prominent companion in the sky. After the cataclysmic impact with Theia, Earth was left as a molten or partially molten sphere. The energy from the impact, combined with the heat from gravitational compression and radioactive decay, had melted much of the planet. But from this molten beginning, Earth would develop the layered structure that defines it today. A dense iron-nickel core at the center, a thick rocky mantle surrounding the core, and eventually a thin crust at the surface. This process of differentiation was one of the most important developments in Earth's early history. To understand planetary differentiation, we need to understand a basic principle of physics. Denser materials sink in liquids, while less dense materials float. This is why ice floats in water, why oil floats on water, and why, in a molten planet, iron sinks while silicate rocks rise. The materials that made up the proto-Earth and Theia before their collision were thoroughly mixed. Planetesimals containing both iron-nickel metal and silicate rock had accreted together, creating a heterogeneous mass. But once this mass became molten, gravity could begin sorting the materials by density. The process of differentiation is sometimes called the iron catastrophe, and the name is well deserved. Iron and nickel, which have densities of about 8 grams per cubic centimeter, are roughly twice as dense as the silicate rocks that form Earth's mantle and crust, which have densities of about 3 to 4 grams per cubic centimeter. In a molten planet, even one as large as Earth, the iron would begin to sink toward the center, while the lighter silicates would rise toward the surface. This process released an enormous amount of additional heat. When dense material sinks and light material rises in a gravitational field, gravitational potential energy is converted into kinetic energy and then into heat. It's similar to how a falling object gains kinetic energy as it falls. which is then converted to heat when it hits the ground. In the case of Earth's differentiation, the falling iron released enough heat to raise the planet's temperature by several thousand degrees. This additional heating ensured that Earth remained molten, creating a positive feedback loop. Heat allows differentiation. Differentiation releases more heat, which allows more differentiation, and so on. The sinking iron didn't descend gently or uniformly. Computer models and laboratory experiments suggest that it likely sank in the form of large droplets or diapires, blob-like masses perhaps hundreds of meters to kilometers across. These iron diapires would have descended through the molten silicate mantle like raindrops falling through air, except that their journey took them thousands of kilometers through molten rock rather than a few kilometers through the atmosphere. As they sank, these iron droplets would have behaved like tiny chemical reactors. Iron is a siderophile element, meaning it has an affinity for bonding with certain other elements. As the iron descended through the mantle, it would have scavenged other siderophile elements, such as nickel, cobalt, and the platinum group elements, carrying them down into the forming core. This chemical partitioning between the mantle and core is why Earth's mantle is relatively depleted in these siderophile elements, while they're concentrated in the core. The formation of Earth's core had several profound implications. First, it created a compositionally distinct layer at Earth's center, fundamentally changing the planet's structure. Second, it set the stage for the development of Earth's magnetic field. The core is divided into two parts: a solid inner core and a liquid outer core. The liquid outer core is in constant motion, driven by convection currents powered by heat escaping from the core. This moving, electrically conductive liquid metal creates Earth's magnetic field through a process called the geodynamo. The magnetic field, in turn, has been crucial for protecting Earth's atmosphere from being stripped away by the solar wind, making it one of the key factors in Earth's long-term habitability. The exact timing of core formation is difficult to determine precisely, but evidence from isotope geochemistry suggests that the bulk of the process occurred very early in Earth's history, probably within the first 100 million years. The Theia impact likely contributed to the final stages of core formation, both by adding Theia's iron core to Earth's core and by remelting Earth and allowing any remaining unincorporated iron to sink to the center. While the core was forming, the mantle was also developing its own structure and composition. The mantle is not a uniform layer of rock, but rather a complex, heterogeneous system with variations in temperature, composition, and mineralogy at different depths. The deep mantle, near the core mantle boundary, experiences temperatures exceeding 3,000 degrees Celsius and pressures more than 1,000,000 times atmospheric pressure at Earth's surface. Under these extreme conditions, minerals undergo phase transitions, rearranging their crystal structures into denser, more compact forms. One of the most important phase transitions occurs at a depth of about 660 kilometers, where the common mantle mineral olivine transforms into a denser crystal structure called wadsleyite, and then, at greater depths, into an even denser form called ringwoodite. At the core mantle boundary, pressures are so extreme that minerals adopt crystal structures that can't exist anywhere else in the solar system except in the interiors of large planets. The mantle also hosts large-scale circulation patterns called mantle convection. Hot material from deep in the mantle rises toward the surface, while cooler material from near the surface sinks. This convection is ultimately driven by the heat escaping from Earth's interior, both the primordial heat left over from Earth's formation and differentiation, and heat continually generated by radioactive decay of elements like uranium, thorium, and potassium in the mantle. In the Hadean mantle convection, would have been much more vigorous than it is today. The Zircon planet was hotter, and higher temperatures mean lower viscosity. Molten or partially molten rock flows more easily when it's hotter. Some models suggest that the Hadean mantle was so hot and actively convecting that it may have been in a state of turbulent convection, with small-scale, chaotic circulation patterns quite different from the organized, large-scale convection cells that characterize the modern mantle. The question of when plate tectonics began on Earth is closely related to the state of the Hadean mantle, and it remains one of the most debated topics in early Earth science. Plate tectonics, the process by which Earth's lithosphere is broken into large plates that move relative to each other, is ultimately driven by mantle convection. But it requires certain conditions to operate. The lithosphere must be cool enough to be rigid, yet the mantle beneath must be hot enough to convect. The lithosphere must also be dense enough to sink when it returns to the mantle at subduction zones. Some scientists argue that plate tectonics could not have operated in the Hadean because the mantle was too hot and convection too vigorous. In this view, the Hadean Earth may have had what's called a stagnant lid regime, where the surface formed a thick, immobile layer while the mantle convected beneath it. Others point to evidence from zircon crystals that suggests some form of plate tectonics may have begun as early as 4.4 billion years ago, very shortly after the Theia impact. This remains an active area of research and debate, with new evidence and models continually refining our understanding. Regardless of when plate tectonics began, the differentiation of Earth into core, mantle, and eventually crust was essential for creating a geologically active planet. The flow of heat from the interior drives volcanism, mountain building, and the recycling of Earth's surface through plate tectonics. The magnetic field generated by the core protects the atmosphere. The chemical differentiation between core and mantle created distinct reservoirs of elements that would later be important for life. By the end of the Hadean, Earth's differentiation was largely complete. The core had formed and begun generating a magnetic field. The mantle had developed its layered structure and begun its slow, churning convection. And at the surface, the first permanent crust was beginning to form, marking the transition from a completely molten world to one with at least some stable, solid ground. One of the most dramatic and important features of early Earth was the magma ocean, a global or nearly global layer of molten rock that covered the planet's surface for much of the Hadean Eon. Understanding this magma ocean and its eventual solidification is crucial for understanding how Earth developed its first crust and began the transition to a more familiar world. The existence of a magma ocean in Earth's early history has been inferred from multiple lines of evidence. The heat generated by the Theia impact alone would have been sufficient to melt most or all of Earth's surface to significant depths. Computer models of the impact suggest that the energy released could have created a magma ocean hundreds of kilometers to perhaps 1,000 kilometers deep. Some extreme models even suggest that the entire mantle might have been molten, creating a magma ocean extending all the way down to the core mantle boundary, some 3,000 kilometers below the surface. A magma ocean is not like a calm lake of molten rock. It would have been a violently convecting, churning mass, with hot plumes of molten rock rising from depth and cooler, denser liquids sinking back down. The surface temperature of this magma ocean would have been extraordinarily high, perhaps 2,000 degrees Celsius or more. At such temperatures, rock doesn't just glow red, it glows white hot, and much of the surface would have been partially vaporized, creating a thick atmosphere of rock vapor above the molten surface. This rock vapor atmosphere would have contained silicon dioxide, magnesium oxide, iron oxide, and various other components of vaporized rock. As Earth cooled, this vapor would have condensed back into liquid droplets that rained down onto the magma ocean surface. Some scientists have described this as a rain of molten rock, droplets of liquid stone falling through a thick, turbulent atmosphere to splash into the magma ocean below. The cooling and crystallization of the magma ocean was not a simple or uniform process. Different minerals crystallize at different temperatures, as described by Bowen's reaction series, a sequence that predicts the order in which minerals will form as a magma cools. The first minerals to crystallize from the magma ocean would have been those with the highest melting points, such as olivine and pyroxene. These are dense minerals, denser than the liquid magma from which they formed, so they would have sunk to the bottom of the magma ocean, forming a layer of solid or partially solid rock at the base. As crystallization continued and the magma ocean cooled, lighter minerals would have begun to form. Eventually, plagioclase feldspar, a relatively low-density mineral, would have crystallized and floated to the surface, forming rafts and eventually a coherent layer of solid crust. This is the same process that formed the Moon's ancient anorthositic crust, and it may have formed a similar crust on early Earth. However, there's a crucial difference between the Moon and Earth. The Moon is small enough that its magma ocean could cool and solidify into a stable crust that has persisted for more than 4 billion years. Earth is much larger, and its internal heat takes much longer to dissipate. Even as the surface of the magma ocean was cooling and forming a crust, the intense heat from the interior was working to remelt that crust from below. This created a dynamic situation where crust would form only to be destroyed and recycled back into the mantle. Convection currents in the still molten mantle would have pulled the newly formed crust downward at some locations, while pushing fresh molten rock up to the surface at others. Large impacts, which were still common during the Hadean, would have repeatedly disrupted and melted any crust that had formed. The Hadean crust would have been unstable, transient, constantly forming and being destroyed in an endless cycle. The composition of this early crust is also a subject of ongoing research and debate. Some models suggest it would have been mafic or even ultramafic in composition, rich in magnesium and iron, similar to modern oceanic crust or even to the mantle itself. This interpretation follows from the idea that the crust would have been formed directly from the cooling of mantle material, without the complex processes that today produce the more silica-rich rocks of continental crust. However, there's intriguing evidence from the Jack Hill's zircon crystals that suggests at least some felsic crust rich in silica, similar to modern continental crust, may have formed very early in Earth's history. Zircons, with ages of 4.4 billion years, have compositions that suggest they crystallized from magmas that were more evolved than simple basalt. This could mean that even in the Hadean, some process was already producing more silica-rich rocks. How could felsic rocks form so early? This question remains open to interpretation. One possibility is that even though the surface was largely covered by a magma ocean, there may have been small islands of solid crust that persisted long enough for more complex geological processes to operate. Water, if it was present, as we'll discuss in a later section, could have played a crucial role. Water lowers the melting point of rocks and changes the sequence of minerals that crystallize from a cooling magma. If water was present in the Hadean mantle, it could have helped produce more evolved, silica-rich magmas even at this early stage. Another possibility involves the role of impacts. When a large asteroid or comet strikes the Earth, it creates immense heat and pressure. This can cause partial melting of the crust and upper mantle. The molten rock produced by this partial melting tends to be more evolved in composition than the original rock, richer in silica and lighter elements. Through this mechanism, repeated impacts could have produced pockets of more evolved crust, even in a largely basaltic or ultramafic early crust. The thickness of the Hadean crust would have varied over time and space. During periods of intense bombardment, the crust may have been thin and discontinuous. During quieter periods, it could have thickened to tens of kilometers. The crust would also have been thinner in regions of upwelling mantle material and thicker in regions where the mantle was descending. One of the most important questions about the Hadean crust is whether it was similar to modern oceanic crust or more like continental crust. This matters because the two types of crust behave very differently. Oceanic crust, being denser, can sink back into the mantle through subduction. Continental crust, being lighter, tends to float on the mantle and is difficult to destroy once formed. If the Hadean crust was oceanic in character, it would have been readily recycled, which could explain why we have no preserved rocks from this time period. If some of it was continental in character, we would expect at least fragments to have survived. The geological evidence suggests that little, if any, Hadean crust survived to the present day. The oldest intact rock formations date to about 4 billion years ago, marking the boundary between the Hadean and Archean eons. This could mean that the Hadean crust was indeed oceanic and mafic in character, readily subducted and destroyed. Alternatively, it could mean that the early crust, regardless of composition, was simply too unstable to persist through the extreme conditions of the late Hadean, particularly the intense bombardment that may have occurred around 4 billion years ago. The transition from a magma ocean world to a world with stable crust was not instantaneous or uniform. Different models predict different timescales for the solidification of the magma ocean, ranging from as little as a few million years to perhaps tens of millions of years. The actual rate would have depended on many factors: the initial depth of the magma ocean, the composition of the rock, the presence or absence of water, the rate of heat loss to space, and the continued input of heat from impacts and radioactive decay. What is clear is that by the end of the Hadean, around 4 billion years ago, Earth had transitioned from a world dominated by molten rock to one with a solid crust, albeit a crust that was probably much more geologically active and unstable than Earth's modern crust. This transition was essential for the next phase of Earth's evolution, because a solid crust is necessary for water to accumulate on the surface, and liquid water, as we'll see, appears to have been present surprisingly early in Earth's history. Earth's atmosphere today is a benign mixture of nitrogen and oxygen, with trace amounts of other gases, the air we breathe without a second thought. But the Hadean atmosphere was radically different, a toxic, unbreathable mixture that would have been instantly fatal to any complex life form. Understanding the composition and evolution of this early atmosphere is crucial for understanding how Earth transformed from a lifeless ball of rock into a world capable of supporting life. The very first atmosphere that Earth possessed, if we can even call it an atmosphere, was likely just the remnant of the solar nebula from which the solar system formed. This primordial atmosphere would have consisted primarily of hydrogen and helium, the lightest and most abundant elements in the universe. However, this atmosphere didn't last long. Earth's gravity was not strong enough to retain these light elements for extended periods, especially while the planet was still hot and being bombarded by solar radiation and the solar wind. Within a few million years, this primordial hydrogen-helium atmosphere would have been lost to space. The loss of this first atmosphere didn't leave Earth airless, however. A second atmosphere, what scientists call a secondary atmosphere, began to form through a process called outgassing. As the magma ocean churned and convected, it released gases that had been dissolved in the molten rock. Similarly, volcanic eruptions, which would have been frequent and intense during the Hadean, brought material from the interior to the surface and released gases into the atmosphere. The composition of this secondary atmosphere would have been very different from the first. Instead of hydrogen and helium, it would have consisted of gases released from the molten rock: water vapor, carbon dioxide, nitrogen, and smaller amounts of other gases like carbon monoxide, hydrogen sulfide, sulfur dioxide, and methane. Notably absent from this list is free oxygen. Molecular oxygen, the gas that makes up about 21% of today's atmosphere, would not become abundant until much later in Earth's history, after the evolution of photosynthetic organisms that produce oxygen as a waste product. Water vapor was probably the dominant component of the early Hadean atmosphere. At the surface, temperatures that prevailed when the magma ocean was still liquid, perhaps 1,000 to 2,000 degrees Celsius, rock would have released enormous amounts of water vapor into the atmosphere. Some of this water came from the original planetesimals that built up Earth, which contained water trapped in their mineral structures. Some may have been delivered later by comets and water-rich asteroids. Regardless of its source, there was a lot of water vapor in the early atmosphere, so much that atmospheric pressure may have been tens or even hundreds of times higher than it is today. This brings us to an interesting paradox. With surface temperatures well above the boiling point of water, how could liquid water exist? The answer lies in the high atmospheric pressure. At Earth's current atmospheric pressure of about 1 bar at sea level, water boils at 100 degrees Celsius. But at higher pressures, the boiling point increases. Research on early Earth conditions suggests that at an atmospheric pressure around 217 times Earth's current pressure, water doesn't boil until it reaches 374 degrees Celsius. Above this pressure and temperature, you reach what's called the critical point, where the distinction between liquid and gas disappears entirely, and water exists as a supercritical fluid. The early Hadean atmosphere may have been thick enough and hot enough that water existed in a supercritical state or remained liquid despite temperatures that would boil it away under current conditions. As the surface cooled, this water vapor would have begun to condense. The first rains on Earth would have been hot, possibly hundreds of degrees Celsius, and would have fallen through an incredibly dense, steamy atmosphere. These weren't gentle spring showers. They were torrential downpours of nearly boiling water, drenching a landscape of partially molten rock. Carbon dioxide was likely the second most abundant component of the early atmosphere. Like water, carbon dioxide was released by volcanic outgassing. Unlike water, carbon dioxide remains a gas at much higher temperatures, so it wouldn't have condensed out of the atmosphere as quickly as water did. At the high concentrations that may have existed in the Hadean atmosphere, perhaps 10 to 100 times the current level, carbon dioxide would have created a powerful greenhouse effect, trapping heat and keeping the surface warm even as the planet began to cool. The role of carbon dioxide in the early atmosphere is crucial because it affects Earth's temperature history. A thick carbon dioxide atmosphere would have kept the surface warm, potentially allowing liquid water to exist even when the sun was dimmer than it is today. The sun has gradually increased in brightness over its lifetime, and during the Hadean, it was about 20 to 30% fainter than today's sun. This greenhouse warming may have been essential for keeping Earth's surface at temperatures suitable for liquid water during the late Hadean and early Archean. Nitrogen, which makes up about 78% of today's atmosphere, was probably present in smaller amounts in the Hadean atmosphere. nitrogen is relatively inert chemically and doesn't easily react with rocks or dissolve in water, so once it was outgassed from the interior, it would have accumulated in the atmosphere. However, the total amount of nitrogen in the early atmosphere is uncertain because we don't know how much nitrogen was present in the materials that built up Earth, or how efficiently it was released through outgassing. The early atmosphere would also have contained a variety of other gases in smaller quantities. Sulfur dioxide and hydrogen sulfide, both of which give volcanoes their characteristic rotten egg smell, would have been released by volcanic activity. Carbon monoxide, a poisonous gas, may have been present if conditions were reducing enough. That is, if there was a shortage of oxygen to convert all the carbon monoxide to carbon dioxide. Methane, a potent greenhouse gas, could have been produced by reactions between water and iron-rich rocks at high temperatures. The chemical state of the atmosphere, whether it was reducing, rich in hydrogen and poor in oxygen, or oxidizing, rich in oxygen, has important implications for understanding early Earth chemistry and the origin of life. Most current models suggest that the Hadean atmosphere was mildly reducing or neutral, rather than strongly reducing. This is based on studies of the oxidation states of minerals in ancient rocks, and on theoretical considerations about the chemistry of outgassing from a magma ocean. The evolution of the atmosphere over the course of the Hadean was complex and nonlinear. Major impacts could have temporarily blown away significant portions of the atmosphere, requiring it to be rebuilt through renewed outgassing. The condensation of water vapor into oceans would have dramatically reduced atmospheric pressure and removed the dominant atmospheric component. Reactions between atmospheric gases and the surface rocks would have altered atmospheric composition over time. For example, carbon dioxide reacts with silicate rocks in the presence of water to form carbonate minerals, effectively removing carbon dioxide from the atmosphere and locking it away in solid rock. As the Hadean progressed and the surface cooled, the atmosphere would have gradually transitioned from a dense, water vapor-rich steam bath to something more recognizable as a traditional atmosphere. By the end of the Hadean, the atmosphere probably consisted primarily of nitrogen and carbon dioxide, with smaller amounts of water vapor, methane, and other trace gases. This was still a far cry from today's oxygen-rich atmosphere, but it was an atmosphere in which liquid water could exist stably on the surface, setting the stage for the next chapter in Earth's story. One final important feature of the Hadean atmosphere was the absence of an ozone layer. Ozone is a form of oxygen that forms high in the atmosphere when molecular oxygen is broken apart by ultraviolet light from the sun. The ozone layer protects Earth's surface from harmful ultraviolet radiation. Without free oxygen in the atmosphere, there could be no ozone layer, which means the surface of Hadean Earth would have been bathed in intense ultraviolet radiation. This has important implications for the origin of life, as we'll discuss later. UV radiation can break apart complex organic molecules, making it harder for life to get started. On the other hand, UV radiation can also drive chemical reactions that create organic molecules from simpler precursors, so its role may have been complex. The Hadean atmosphere, toxic and unbreathable though it was, played crucial roles in Earth's development. It helped regulate surface temperature through the greenhouse effect. It delivered water to the surface through condensation and rain. It provided raw materials, carbon, nitrogen, and hydrogen, that would later be essential for life, and it protected the surface from the worst extremes of space, even without an ozone layer providing some shielding simply through its mass. The presence of liquid water on Earth's surface is one of the defining characteristics of our planet, and one of the key factors that made Earth habitable for life. But when and how did Earth's oceans form? For decades, scientists assumed that during the Hadean, the supposed hellish eon, the surface was too hot for liquid water to exist. Recent evidence has challenged this assumption and suggests that oceans may have formed much earlier than previously thought, perhaps as early as 4.4 billion years ago, just 200 million years after Earth's formation. The story of Earth's water begins with the question of where it came from. This might seem like a simple question with an obvious answer. Water must have been present in the materials that built up Earth. But the reality is more complex. The temperature in the inner solar system during planet formation was high enough that water ice couldn't condense close to the sun. The rocky planetesimals that built up Earth and the other inner planets would have been largely devoid of water ice. So where did Earth's water come from? One possibility is that water was present in the minerals that made up these planetesimals, not as ice, but locked into the crystal structure of certain minerals. Minerals can contain small amounts of water, either as hydroxyl groups bonded into the crystal lattice or as tiny fluid inclusions trapped within the mineral. When these minerals were melted during impacts or during the differentiation of Earth's interior, the water would have been released. Laboratory studies of meteorites, the remnants of planetesimals that never grew large enough to become planets, show that even meteorites from the inner solar system contain small but measurable amounts of water, typically around 0.1% by weight. If the planetesimals that built up Earth had similar water contents, and if this water was efficiently released during Earth's formation and differentiation, it could account for a significant fraction of Earth's current ocean mass. Another source of water was likely comets and asteroids from the outer solar system. Comets, in particular, are rich in water ice. They're essentially dirty snowballs, with ice making up a large fraction of their total mass. During the late stages of planet formation and the subsequent bombardment period, countless comets would have struck Earth, delivering their ice to the surface. When a comet, traveling at tens of kilometers per second, impacts a planet, the ice is vaporized by the heat of the impact, adding water vapor to the atmosphere. The isotopic composition of water provides clues about its source. Water molecules contain hydrogen and oxygen, and both elements have multiple isotopes. The ratio of deuterium, heavy hydrogen with one neutron, to regular hydrogen in water varies depending on where and how the water formed. By measuring these isotope ratios in Earth's oceans and comparing them to the ratios in meteorites and comets, scientists can constrain which sources contributed to Earth's water. These studies suggest that Earth's water most closely matches the composition of certain types of asteroids, particularly a class called carbonaceous chondrites. Comets, by contrast, tend to have higher deuterium to hydrogen ratios, suggesting they may have contributed less to Earth's water budget than once thought. However, significant uncertainty remains, and it's quite possible that multiple sources contributed to Earth's oceans in varying proportions. Regardless of where the water came from, the question remains: when did it accumulate on the surface as liquid oceans? The traditional view held that during the Hadean, Earth's surface was too hot for liquid water. The magma ocean would have vaporized any water, keeping it in the atmosphere as steam. Only after the magma ocean had solidified and the surface had cooled below the boiling point of water could oceans form. This changed with the discovery and analysis of the Jack Hill's zircon crystals. These tiny mineral grains, some dating back to 4.4 billion years ago, contain chemical signatures that strongly suggest they formed in the presence of liquid water. Zircons crystallize from cooling magma, and the chemistry of the magma from which they crystallize depends on many factors, including whether water was present. The Jack Hill's zircons have oxygen isotope ratios that indicate they came from magmas that interacted with surface water. Strong evidence that liquid water existed on Earth's surface far earlier than previously thought. How could liquid water exist on a surface that was supposedly molten or nearly molten? Several factors may have allowed this apparent paradox. First, as we discussed in the previous section, high atmospheric pressure raises the boiling point of water. Even at temperatures of several hundred degrees Celsius, water can remain liquid if the atmospheric pressure is high enough. The early Hadean atmosphere may have been so thick that water remained liquid, despite surface temperatures that would boil it away under modern conditions. Second, the cooling of the magma ocean may have been faster than early models predicted. Once the surface began to solidify, heat could only escape through conduction, through the solid crust, and through volcanic activity. This is much less efficient than direct radiation from a molten surface. But it also means that once the surface started to solidify, it could cool relatively quickly, dropping below the critical temperature for liquid water within just a few million years. Third, even if much of the surface remained molten, there may have been cooler regions, perhaps at the poles or in the shadows of large volcanic edifices, where water could condense and accumulate. The zircons we've found may have formed in these localized environments rather than representing global conditions. If liquid water did exist on the surface as early as 4.4 billion years ago, what were these early oceans like? They would have been dramatically different from today's oceans in several ways. First, they would have been hot, perhaps not boiling, but certainly much warmer than modern ocean water. Based on atmospheric pressure models and the boiling point of water under those conditions, temperatures of 50 to 100 degrees Celsius or more seem plausible for early Hadean oceans, though the exact values remain uncertain. Second, the early oceans would likely have been acidic to some degree. The atmosphere contained high concentrations of carbon dioxide and other acidic gases like sulfur dioxide. When these gases dissolve in water, they form acids, carbonic acid in the case of carbon dioxide, sulfuric acid in the case of sulfur dioxide. While the exact pH remains uncertain, some researchers have suggested the early oceans may have been significantly more acidic than modern seawater, possibly with a pH low enough to rapidly weather and dissolve rocks. Third, the early oceans would have been rich in dissolved minerals. The acidic water reacting with the basaltic crust would have leached out various elements, including magnesium, calcium, iron, and silica. This would have made the early oceans chemically very different from modern seawater, which is dominated by sodium and chloride ions. Fourth, the early oceans may have been deeper and more extensive than modern oceans. Some models suggest that in the early Hadean, before significant continental crust had formed to create landmasses, Earth may have been entirely covered by a global ocean. This ocean-planet scenario is supported by some of the evidence from the Jack Hill's zircons and fits with models of early crustal formation. The interaction between the early oceans and the hot crust below would have created extensive hydrothermal systems. Wherever seawater percolated down through cracks in the crust and encountered hot rock, it would have been heated, causing minerals to dissolve and chemical reactions to occur. This heated water would then rise back to the surface, carrying dissolved minerals with it. Modern hydrothermal vents at mid-ocean ridges provide a glimpse of what these early systems might have been like, though the Hadean versions were probably much more extensive and active due to the higher heat flow from Earth's interior. The presence of liquid water on the surface would have had profound effects on Earth's geological and chemical evolution. Water changes the melting behavior of rocks, lowering the melting point and altering the composition of magmas that form through partial melting. This may have been crucial for for the formation of the first continental crust. Water also facilitates chemical weathering of rocks, breaking down minerals and creating clays and other secondary minerals. The products of this weathering would have accumulated as sediments on the ocean floor, potentially forming some of the earliest sedimentary rocks. Water in the oceans and in the crust also affects plate tectonics. Subduction, the process by which oceanic crust descends back into the mantle, is facilitated by the presence of water, which makes the descending slab less viscous and helps it sink. Some scientists argue that the presence of oceans in the Hadean may have been necessary for plate tectonics to begin. Perhaps most importantly, for the story of life, liquid water provided an environment where complex chemistry could occur. Many of the chemical reactions that are thought to be important for the origin of life require liquid water. Water is a solvent that allows molecules to dissolve and interact. It's also a reactant in many important biochemical processes. The presence of liquid water on Earth's surface, possibly as early as 4.4 billion years ago, meant that the chemical preconditions for life were in place far earlier than once thought possible. The early oceans were not static. They would have been affected by continued impacts from asteroids and comets. Large impacts could have temporarily boiled away portions of the ocean, vaporizing the water and sending it back into the atmosphere, from which it would later recondense. Very large impacts might have evaporated the entire global ocean, a process that would take perhaps hundreds to thousands of years to reverse. But in the intervals between these catastrophic events, liquid water persisted on Earth's surface, creating a potential haven for the chemistry that would eventually lead to life. Throughout the Hadean Eon, Earth and the other planets in the inner solar system were subjected to a constant rain of asteroids, comets, and other debris left over from planet formation. But evidence suggests that this bombardment may have intensified dramatically near the end of the Hadean, in an event known as the Late Heavy Bombardment, or LHB. Understanding this event is crucial for understanding the environment in which life first emerged on Earth. The evidence for the Late Heavy Bombardment comes primarily from the Moon. When astronauts from the Apollo missions brought back samples of lunar rocks, scientists were able to date them using radiometric techniques. What they found was surprising. A large number of impact melt rocks that had been melted by the heat of asteroid impacts, had ages clustered around 3.9 billion years ago. This clustering suggested that the Moon, and by extension, the entire inner solar system, experienced a spike in impact rates at this time. The lunar surface today is covered with craters, the scars of billions of years of impacts. The largest of these are called impact basins, massive craters hundreds or even thousands of kilometers in diameter. The mare, the dark regions visible on the Moon's face, are these basins filled in by lava flows that erupted after the impacts. Dating of samples from several of these basins, the Imbrium Basin, the Serenitatis Basin, the Nectaris Basin, showed that they all formed within a relatively narrow time window, around 3.8 to 3.9 billion years ago. The Late Heavy Bombardment hypothesis proposes that this clustering of ages reflects a real increase in the bombardment rate, rather than just being a sampling bias or statistical artifact. According to this hypothesis, for the first 600 million years of solar system history, the impact rate was relatively low, or at least declining steadily as the planets swept up the debris in their orbital zones. Then, around 4.1 to 3.9 billion years ago, something disturbed the orbits of countless asteroids and comets, sending them careening into the inner solar system where they collided with the terrestrial planets. What could have caused such a disturbance? The most widely accepted explanation is the Nice model, named after the French city where it was developed. According to this model, the giant planets Jupiter, Saturn, Uranus, and Neptune did not form in their current orbits. Instead, they formed closer together and gradually migrated outward through gravitational interactions with the disk of debris that still surrounded the Sun. At some point, perhaps 600 million years after the solar system formed, these migrations caused Jupiter and Saturn to enter a special orbital configuration called a 2-to-1 resonance, where Jupiter completed exactly 2 orbits for every 1 orbit of Saturn. This resonance destabilized the orbits of Uranus and Neptune, causing them to suddenly migrate outward into the outer regions of the solar system. As they plowed through this region, they scattered countless icy bodies, sending some flying out of the solar system entirely, while flinging others into the inner solar system. These scattered objects bombarded the terrestrial planets, creating the spike in impacts that we see recorded in the lunar rocks. The NICE model is elegant and explains many features of the solar system's architecture, but the late heavy bombardment hypothesis remains controversial. Some scientists argue that the clustering of lunar impact ages could be an artifact of sampling. We've only visited a small portion of the moon's surface, all within or near large impact basins, so we may be seeing a biased sample. According to this alternative view, there was no spike in impact rates. Instead, the bombardment declined smoothly over time, and the clustering of ages around 3.9 billion years simply reflects the formation of a few large basins that happened to occur around that time. More recent analyses of lunar samples have added complexity to the picture. Some studies have found evidence for impacts extending back to 4.2 billion years ago and beyond, suggesting that if there was a late heavy bombardment, it may have been more extended in time than originally thought. Other analyses have found that some impact melt rocks thought to date from the LHB may actually have been contaminated by material from younger impacts, making their ages less certain. Regardless of whether there was a discrete spike in impacts or a more gradual decline in bombardment, it's clear that the late Hadean and early Archean were times of intense impact activity. Earth, being larger than the moon, would have been hit by even more impactors. Computer models estimate that during this period of heavy bombardment, Earth may have been struck by 1 to 4 objects larger than 600 miles, roughly 1,000 kilometers in diameter, asteroids larger than the dwarf planet Ceres, and by several additional objects in the 100 to 1,000 kilometer size range. What were the effects of these impacts on Earth? The largest impacts would have been truly catastrophic events. An object 1,000 kilometers across striking Earth at a typical velocity of 20 kilometers per second would release enough energy to vaporize a large portion of Earth's oceans. The impact would excavate a crater hundreds of kilometers deep and thousands of kilometers across. The heat from the impact would be sufficient to melt a substantial fraction of Earth's crust, creating a global or near-global magma ocean. The atmosphere would be affected dramatically. The impact would blast enormous quantities of material, both from the impactor and from Earth's crust, into the atmosphere and beyond. Much of this material would fall back to Earth, re-entering the atmosphere at high velocities and heating the atmosphere through friction. For hours or days after the impact, the entire sky would glow red hot as this material rained back down. Surface temperatures could spike to 500 degrees Celsius or more, essentially sterilizing the entire surface of the planet. However, several factors might have mitigated the destructive effects of these impacts. First, the impacts, while individually catastrophic, were separated by long intervals of time. Even at the peak of the bombardment, tens of thousands or hundreds of thousands of years might pass between the very largest impacts. This would have given the surface time to cool and the environment time to recover between events. Second, while the surface would have been sterilized by the largest impacts, life, if it had already emerged, might have survived in subsurface environments. Computer models show that even the largest impacts would only sterilize the top few hundred meters of the crust. Below this depth, the temperature increase would be much less severe. Microorganisms living in cracks and pores in the rock, perhaps around hydrothermal systems deep underground, could have survived and recolonized the surface once conditions permitted. Third, and perhaps most paradoxically, the impacts may have actually been beneficial for the emergence of life in some ways. Impacts create hydrothermal systems by heating and fracturing rocks, allowing water to circulate through them. These hydrothermal systems could have provided energy and nutrients for early life. Impacts also deliver organic compounds, the carbon-based molecules that form the basis of life. Meteorites and comets contain amino acids, sugars, and other organic molecules. And while most of these would have been destroyed by the heat of impact, some fraction might have survived and contributed to the pool of organic material on early Earth. Some scientists have proposed that impact craters themselves might have been favorable environments for the origin of life. A large impact crater would create a deep basin that could fill with water, creating a protected environment. The hydrothermal circulation around the crater could provide energy and drive chemical reactions. The fractured rocks in and around the crater would provide mineral surfaces that could catalyze reactions. All of these factors might have made impact craters the ideal locations for life to emerge. The late heavy bombardment also had important implications for the delivery of water to Earth. While most of Earth's water probably arrived during the main accretion phase, the continued bombardment during the late Hadean and early Archean would have delivered additional water. Comets, in particular, are rich in water ice, and while their isotopic composition doesn't perfectly match Earth's water, they may have contributed to the late-stage buildup of Earth's oceans. The bombardment also affected the rate at which the crust could accumulate and persist. Every large impact would have disrupted or destroyed significant portions of the crust. This is one reason why we have no preserved rocks from the Hadean. Any crust that formed would have been repeatedly melted or fragmented by impacts. Only after the impact rate declined significantly, marking the transition to the Archean Eon around 4 billion years ago, could a stable, permanent crust begin to develop. As we'll discuss in the next section, the Hadean bombardment, whether it was a discrete, late heavy event or a more gradually declining tail, has left us with precious little direct evidence. But that evidence, in the form of ancient zircon crystals, provides tantalizing glimpses of what Earth was like during this violent period. Given the scarcity of Hadean rocks, how can we know anything about this ancient time? Our most important source of information comes from tiny crystals called zircons, found in a remote region of Western Australia known as the Jack Hills. These zircons are truly remarkable. They are the oldest known materials of terrestrial origin, time capsules preserving information about Earth's earliest history. The Jack Hills themselves are not particularly imposing, a range of low, weathered hills in the arid interior of Western Australia, about 800 kilometers north of Perth. But this unremarkable landscape holds extraordinary treasures. In the 1980s, geologists studying ancient sedimentary rocks in this region began finding zircon crystals with ages far older than the rocks that contained them. This makes sense. The sedimentary rocks were formed from the erosion and redeposition of even older rocks. The zircons, being extremely durable, survived the destruction of those ancient rocks and were incorporated into the younger sediments. Zircons are tiny, typically only 1/10 of a millimeter or so in size, about the width of a human hair. But they are incredibly tough. Chemically, they are zirconium silicate with a formula of ZrSiO4. This crystal structure is extremely resistant to both chemical weathering and physical deformation. Zircons can survive being eroded from rocks, transported by rivers, buried, subjected to high temperatures and pressures during metamorphism, and exhumed back to the surface, all while maintaining their original internal structure and chemistry. This durability is what makes zircons so valuable for geochronology, the study of the age of rocks and minerals. Zircons incorporate uranium into their crystal structure when they form, but they exclude lead. Over time, the uranium atoms undergo radioactive decay, transforming into lead through a series of steps. By measuring the ratio of uranium to lead in a zircon, scientists can calculate how long ago the zircon crystallized. This uranium-lead dating method is one of the most accurate and reliable dating techniques available. Among the thousands of zircons found in the Jack Hills sediments, a few are extraordinarily ancient. The oldest confirmed zircon has been dated to approximately 4.4 billion years ago. Some studies report 4.404 billion years, with an uncertainty of about 8 million years. This suggests it crystallized just 160 million years or so after the formation of the solar system itself, and roughly 100 million years after the Theia impact that formed the moon. Other zircons from the Jack Hills span a range of ages from about 3 billion years to more than 4.4 billion years, providing a discontinuous but invaluable record of Earth's early history. The ages alone would make these zircons interesting, but they offer much more than just dates. The chemistry of the zircons can tell us about the environment in which they formed. When a zircon crystallizes from cooling magma, it captures chemical signatures that reflect the composition and temperature of that magma and the conditions under which the magma formed. One of the most important discoveries from the Jack Hills zircons involves oxygen isotopes. Oxygen has 3 stable isotopes: oxygen-16, oxygen-17, and oxygen-18. The ratio of oxygen-18 to oxygen-16 varies depending on temperature and on whether water is present. When scientists measured the oxygen isotope ratios in the ancient Jack Hills zircons, they found values that indicated the magmas from which these zircons crystallized had interacted with water at relatively low temperatures, temperatures typical of Earth's surface rather than of the deep mantle. This was revolutionary. It suggested that by 4.4 billion years ago, Earth had cooled enough for liquid water to exist on its surface. The magmas that produced these zircons had interacted with this surface water, perhaps through weathering and erosion of surface rocks that were then incorporated into the magma, or through direct interaction between magma and surface water in hydrothermal systems. Other chemical signatures in the zircons support this interpretation. The zircons contain mineral inclusions, tiny fragments of other minerals trapped inside the zircon as it grew. These inclusions include minerals like quartz and feldspar, which are typical of more evolved, silica-rich magmas, rather than the primitive basaltic magmas that would form directly from mantle melting. This suggests that even in the Hadean, some process was producing more evolved crustal rocks, possibly through the weathering and remelting of earlier crust in the presence of water. Some of the most controversial findings from the Jack Hills zircons involve possible evidence of life. In 2015, scientists reported finding tiny inclusions of graphite, pure carbon, inside a 4.1 billion-year-old zircon from Jack Hills. The carbon isotope ratio of this graphite was unusually light, depleted in carbon-13 compared to carbon-12, in a way that's characteristic of biological processes. If this interpretation is correct, it would push back the earliest evidence for life on Earth by several 100 million years. However, this finding remains highly controversial. Critics point out that carbon isotope ratios can be affected by many processes, not all of them biological. The tiny size of the graphite inclusion makes it difficult to rule out contamination from younger carbon. And even if the light carbon isotope ratio is real and ancient, it might reflect non-biological processes that can also fractionate carbon isotopes. Most scientists consider this evidence suggestive, but not conclusive proof of early life. The Jack Hills zircons also provide information about impact bombardment. Some of the zircons show evidence of having been subjected to shock, the sudden, intense pressures that occur during an impact. By dating these shocked zircons, scientists can constrain the timing of large impacts. Other zircons show evidence of having been heated to high temperatures after they initially formed, which could also reflect impact events or other geological processes. The geographical distribution of Hadean zircons is itself informative. So far, nearly all of the very oldest zircons have come from just one locality, the Jack Hills in Western Australia. A few Hadean zircons have been found in other locations, such as in the Acasta gneiss of northern Canada and in rocks from South America and Africa. But these are relatively rare. This scarcity has two possible explanations. Either Hadean rocks and zircons were rare to begin with, or most have been destroyed by subsequent geological processes, and we've only found the few that survived by chance. The study of the Jack Hills zircons continues to advance as analytical techniques become more sophisticated. New methods allow scientists to analyze smaller and smaller portions of individual zircons, revealing details about zonation within single crystals that can tell us about changing conditions during growth. Advanced dating techniques using atom probe tomography can map the distribution of individual atoms within the zircon, allowing for even more precise age determinations and better understanding of any processes that might have disturbed the uranium-lead system after the zircon formed. These tiny crystals have revolutionized our understanding of the Hadean Eon. They have overturned the traditional view of the Hadean as a continuously hellish period. Instead, they paint a picture of a world that, while certainly more violent and geologically active than modern Earth, was also capable of hosting liquid water on its surface and perhaps even some form of primitive crust. They suggest that the transition from a molten world to a habitable world happened much faster than scientists once believed. Yet for all they tell us, the Jack Hills zircons also highlight how much we don't know. These are individual crystals, each recording only a moment in time from a specific location. They provide snapshots, not a continuous record. Many fundamental questions remain unanswered. How extensive was the early ocean? What was the composition and thickness of the early crust? When did plate tectonics begin? Did life exist in the Hadean? The zircons give us hints and constraints, but definitive answers to these questions remain elusive. As the Hadean Eon drew to a close around 4 billion years ago, Earth had been transformed from its birth state into something far more complex and dynamic. The transition from the Hadean to the Archean Eon wasn't marked by a single catastrophic event, but rather represented a gradual shift in conditions as the planet continued to evolve. By the end of the Hadean, Earth had developed most of the features that would characterize it for the rest of its history. The core had formed and was generating a magnetic field that helped protect the atmosphere from being stripped away by the solar wind. The mantle had differentiated into layers with distinct compositions and behaviors. A thin but stable crust had begun to form, providing solid ground on the surface for the first time in Earth's history. The atmosphere had evolved from a dense steam bath, dominated by water vapor and carbon dioxide, into a thinner, nitrogen-rich atmosphere, though still lacking the free oxygen that would characterize later atmospheres. The condensation of water vapor had created oceans that covered most or all of the planet's surface. These oceans were hot, acidic, and chemically very different from modern oceans, but they were stable enough to persist for extended periods. The impact bombardment, while still ongoing, had declined from the intense pounding of the earlier Hadean. Whether there was a discrete, late heavy bombardment or a more gradual decline, by 4 billion years ago, the largest impacts were becoming rarer, allowing the crust to accumulate and persist, rather than being repeatedly melted and destroyed. The geological processes that would shape Earth for the rest of its history were beginning to operate. Volcanism brought material from the interior to the surface, releasing gases into the atmosphere and building volcanic landmasses. Water cycled between the oceans and the atmosphere through evaporation and precipitation. Weathering of rocks created sediments that accumulated on the ocean floor. And while the question of when plate tectonics began remains controversial, some form of crustal recycling was likely occurring by the late Hadean or early Archean. Most importantly, for the story we're telling, the stage was set for life. Liquid water existed on the surface. The atmosphere, while toxic to modern organisms, contained the raw materials, carbon, nitrogen, hydrogen, necessary for building organic molecules. Energy was abundant in multiple forms: solar radiation, heat from hydrothermal vents, chemical energy from reactions between rocks and water. Mineral surfaces provided sites where molecules could concentrate and react. Protected environments, such as hydrothermal vents, tidal pools, or pores in rocks, offered refuges where delicate chemical processes could proceed without being disrupted by impacts or harsh surface conditions. The transition from the Hadean to the Archean is defined somewhat arbitrarily. There's no rock record precisely at the boundary. The oldest intact rock formations date to about 4 billion years ago, and there's a gap between these and the Jack Hill's zircons. But around 4 billion years ago, conditions had stabilized enough that crust could form and persist. The Archean would see the development of stable continental blocks, the evolution of the first life forms sophisticated enough to leave fossils, and the beginning of the great oxygenation that would eventually transform Earth's atmosphere. The Hadean deserves its name. It was indeed a time of extreme conditions, of molten surfaces and violent impacts, of an atmosphere that would kill us instantly and oceans hot enough to scald. But it was also a time of creation, of the birth of a world. The processes that shaped the Hadean, accretion, differentiation, outgassing, water delivery, impact bombardment, were not unique to Earth. They happened on all the terrestrial planets and continue to happen on newly forming planets around other stars. What made Earth special was the particular combination of size, composition, orbital location, and cosmic accident. The Theia impact that created our oversized moon, that allowed it to evolve into a habitable world. Earth was large enough to retain an atmosphere and sustain internal heat and geological activity for billions of years, but not so large that it became a gas giant. It orbited at just the right distance from the sun, close enough to remain warm, but not so close as to lose all its water. The Theia impact, while catastrophic, left Earth with a fast initial rotation and a large stabilizing moon. These factors, combined with countless others, created the conditions that would eventually allow life to emerge and flourish. The Hadean Eon reminds us that the Earth we know today is not eternal or unchanging. Our planet has undergone dramatic transformations throughout its history. The comfortable, habitable world we live on was born from chaos and violence. The air we breathe, the water we drink, the ground beneath our feet, all are products of processes that unfolded over hundreds of millions of years during the Hadean and the eons that followed. Studying the Hadean also helps us understand planet formation and evolution in general. Every rocky planet in the universe goes through something similar to a Hadean period, a time of accretion, differentiation, bombardment, and gradual cooling. By understanding Earth's Hadean, we gain insights into how planets form and evolve, which helps us interpret observations of exoplanets orbiting distant stars and evaluate their potential habitability. The Hadean Eon ended not with a bang, but with a gradual transition. The oldest rock formations, the Akasta gneiss in northern Canada, the Isua Greenstone Belt in Greenland, rocks in southern Africa and Western Australia, preserve a record of the early Archean, a world that was still hot, still geologically violent, but increasingly stable and increasingly hospitable. Based on fossil evidence, we know that microbial life had emerged by at least 3.5 billion years ago, though it may have originated earlier, perhaps even during the late Hadean itself. As we look back across the vast gulf of deep time to the Hadean Eon, we see the origins of our world. We see violence and creation intertwined. We see a planet being born, struggling through a difficult infancy, and emerging as a world with the potential to host the most remarkable phenomenon we know of in the universe: life itself. The Hadean was not a failed beginning or a waste of time. It was the essential foundation upon which everything that followed was built. And so, the story of the Hadean Eon ends where the story of life begins. The hellish world has cooled. The magma ocean has solidified into rock. The steam atmosphere has condensed into seas. The cataclysmic bombardment has subsided to a more manageable rate. And in those warm, mineral-rich waters, in the shelter of hydrothermal vents, or in tidal pools or in pores within rocks, the first self-replicating molecules are beginning to stir. The age of biology is about to begin. But that's a story for another time. Thank you so much for joining me on this journey through deep time. If you enjoyed exploring Earth's violent birth and dramatic early history, please consider liking this video and subscribing to The Drowsy Naturalist for more explorations of science and natural history. Sweet dreams and sleep well.